Welcome everyone to part 3 of From Dynamics to Feedback with Uncertainty of the Akreon tutorial series. In this section, I'm going to walk through the open loop system and state feedback control. I'm actually only going to use the feasibility here, though linear objectives and quadratic objectives are valid. Feasibility just kind of just shows you how the synthesis will actually carry out. Just note that the objective function is just going to be 0, so that's not actually going to be per se minimizing anything. It's only going to, the solver that I've set up is only going to abide by the constraints that are imposed by the linear matrix inequalities, and I think it's just that for the state feedback control. All right, so let's move on. The first part here, really is just boilerplate imports of Python modules for this notebook. Right here you can see that there's Akreon Cartpole controls. So what I've done internally is I've built a conic solver, and the first application layer there is a controls facing application suite, if you will. And then the Akreon Cartpole is essentially this system that we derived the equations of motion for, but the controls here are agnostic towards that system. It's just basically getting the dimensions of, if I'm doing the state feedback, the state space matrix correctly. Once we get to H2 and further, like H infinity, which won't be in this tutorial series, you want to have more port allocations, so like where the disturbance channels enter the plant versus the control inputs, and likewise performance outputs versus nominal output. So those are tailored, and it's all templated, highly constant expert, C++ that I, basically packaged into a nice Python module for this video series. If you want to see it, please reach out to me. I'd be more than happy to engage with you on it. So that's a quick spiel there. So I'm walking through state feedback, state observers, H2, optimal control, and then the polytopic versions of that for when we consider uncertainty. The next part here are just nice diagnostics, like plotting utilities. The shadow price in particular is one that I think is a pretty unique one in the sense of, again, with the core engine that I have, you can essentially, because I have my own disciplined convex programming layer, DCP, similar to what CVX is, I can basically drill down all the way to these primal and dual cones, get what those variables are doing in the solving loop, and then back them out up to the constraints that are formulated at this surface level. And so the shadow pricing basically just tells you which conditions, it's basically a complementary slackness kind of utility where you get to see where the primal, variable lies relative to the dual, and you get to see what constraints are slack, what's tight, where's economic utility, could that be gained anywhere if we lessened constraints. For controls here, it's fairly benign, but it is nice to just kind of get this utility and see what it looks like. These are just, plotting rollout states of the gymnasium simulation of the Cartpole. And just note, like, the Cartpole in gymnasium is discrete, so it kind of mirrors more or less like a bang control, which I'll talk about later. But for the state space modeling and the control feedback, all of that is posed in continuous time. And then, of course, if we wanted to move it to discrete time, we could do the 0 order hold, and then we can package it nicely using the Python control module up here. So let's run this to get the imports in, and then this part here shows you all the controllers that I've built for this system. So you can see like nominal feedback, nominal observer. We have state feedback in the observer variance with the polytopic uncertainty modeling. I'm not going to step into those for this video. I'm mainly doing the state feedback, state observer, H2, and then the polytopic versions. For a separate video series, I think I'm going to do the H infinity and mixed synthesis out here with the polytopic versions perhaps, which shows more or less the worst case conditions, trying to basically push down on that and ensure that the solver, our controllers, attenuates any of those, high frequency noises, or, has higher gain in the bandwidth, the target bandwidth that we actually want to control the system. But for right now, pretty simple: state feedback, state observer, H2. So let's move forward. So the open loop analysis here, this is collected from the linearization of the Cartpole, which was the second video, after doing the Euler-Lagrangian dynamics modeling of the system and linearizing about the upright position, the pendulum that is. So that's just plug and play here. That's our A state transition matrix. That's our control matrix B here. And then the state vector, just note that I'm using Z as that state vector variable. The cart position is X, the cart velocity is X dot, angular displacement of the pendulum with respect to the vertical is theta, and then theta dot is the angular rate of the pendulum. So the continuous state space model is Z dot is equal to AZ plus BE. Cool. So in this little code section here, I'm acquiring the parameters from Gymnasium here with, these are just state labels for plotting later on. But you can get the, the mass of the cart, the pole, and remember that there's no inertia term with the pole. It's basically like just a point mass rigidly attached to the center of mass of the cart. Pole length, gravity constant, and then the dt term. Alright, so now I'm plugging them in actually, so A, B, C, D, and just note here with the C matrix, what I'm actually doing here is, in real life you don't necessarily have sensors that are directly sensing a particular variable in our state space. Which would be like an C, which would basically just be full state feedback without any kind of observer needed. This is taking that next step of essentially saying we have a sensor on the cart position, we have a sensor on the angle of displacement, we can observe basically, we'll see observability in a bit, but from these two sensors we can extract and get full observability on our state space with the X dot and theta dot, just with these two measurements here. And that'll just be kind of just more interesting to see what that looks like when we tie the observer feedback into the loop where it's not just full state. And then D's are feed through, and that's just zeros, so there's no input going to the output. And here's our Cartpole state space ABCD, and then I've just logged it out here. All right, cool. So the next part is, I would say, standard in like a controls practitioner's book is to, let's start analyzing the open loop system with respect to the poles of the system. And that would be our eigenvalues. So we can see that we have right half plane, eigenvalue 2 at the origin, and then there's a complex conjugate that is on the left-hand plane. So open loop is unstable, which intuitively makes sense. It's under actuated system. We're not, the pendulum basically is highly sensitive. When I go to this next part of controllability, we can see how the degrees of which the pendulum can be controlled. But at least in this open loop, pretty simple, benign case, it's unstable. So now let's see if we can control the system. So the first method is we can look at Cayley-Hamilton's controllability matrix here. So this is just a simple yes or no binary answer to the question, is the rank of C equal to N? So N is our number of states, and C here is this kind of concatenated matrix where you have the input matrix, and then you have the state transition multiplied by the input matrix, and then polynomial of A, right after that, concatenated together. So you have this essentially short, you have this fat, long matrix, or short and fat. So essentially, when we're testing rank here, let's be careful. This is the full row rank of C. Obviously, we don't care about being like A. It's having all these different columns. If you were to put a vector on this right hand side here, it's going to be esoterically like big and long or whatever. So we only care about the row rank of C being full row rank matching N here. And that's kind of the question, is this system controllable? So we can use CTRB in the Python control library to get the controllability matrix, and then we get the matrix ranks by NumPy. So we can see the controllability rank is 4. So the system is controllable. It's underactuated, but it is controllable. And that's a good, quick yes-no answer. It's up to some numerics, and it's also not the highest degree of fidelity of understanding, what states could be controllable more than other states. And so that's what we go into this next part, which is the controllability gradient, which is important because this is essentially a little bit of the bedrock for state feedback and then moving forward, because it does give us this degree of controllability that we want to understand about the system. So what do we mean by this? So when we measure how unit input energy spreads into the state over a time horizon, so it's an integral. So the controllability gradient integrates over the input effects over time, assuming just a unit input. B is our state, B is our input matrix, and so the outer product here tells us how strongly input enters the system. And then the EAT is basically, the nominal, ordinary differential equation, how, state dynamics evolve over time. The big A is just a linear system, so EAT. So describing how the linear system dynamics naturally evolve over time. So, putting it all together, this controllability gradient tells us what directions the state space are easy or hard to reach with unit input energy. So large gradient directions are easier to move, but that also means that they're more sensitive, right? And then likewise, the small gradient directions are harder to move and less sensitive. So before I kind of step into this next block of code, you can kind of just imagine the Cartpole system. The cart has mass, the pendulum has mass too. The forcing function is acting on the cart. So the cart itself is going to be essentially what's less sensitive, harder to move. The pendulum, because it also has gravity on it, so we have a normal force counteracting the cart. The pendulum, though, has gravity pulling down on the pendulum, this like little point mass guy. But we also have this forcing function too, which impacts that state, right? So that's going to be way more sensitive, and it's also going to be much easier to move. So, and we're going to see that stepping through this controllability gradient code here. So stepping through it really quick, this integrand here is just plucking out this math in between the integral here. This is basically stepping through the different time horizons here, so 0.25, 0.5, etc. to 2.25 for integration time, so we get to see how much energy gets pumped into the system over time at individual scales. So I'm going to plot that, and then this eigenvalue sweep is essentially where I'm getting the eigenvalues of the controllability gradient at these integrated time steps. And then this dominant state impact, that's where, when I was insinuating before, the large gradient directions are easy to move, more sensitive, whereas the small gradient directions are hard to move, less sensitive. So essentially here, this dominant state impact It's posed in a way that's kind of like kinetic energy surrogate, where this eigenvector here is squared, and the eigenvector is basically that translation between the states that we have in our linear system and the eigenspace, and that eigenspace is where the eigenvalues live. So when you have the eigenvalue scaling these eigenvectors, you get this sort of ellipsoidal, high-dimensional, like kind of construct where you get to see which modes dominate the state evolution, provided the control input. And then that essentially tells you what directions are really easy to move in, what's really hard to move in. And so, like I said, kind of mirrors this kinetic energy. It's terminology. It's not obviously one-to-one because x squared and theta squared is not a velocity, but it's good for showing some intuition. So we have the eigensweep here. We have the dominant state impact sweep there. And so this next part is actually plotting the Gramian modes side by side. So on the left-hand side, it'll be the eigenvalues, basically graphed over time. And I should say, yeah, so it'll be all four eigenvalues plotted over time. And then for the dominant state impact, because this is ordered, I'm getting the largest eigenvalue, so the most dominant eigenvalue of our system, and then scaling its associated eigenvector energy-wise, and that's this dominant mode plot here. And that's going to be like a heat map, and I'll show you the states and how the impact of unit input energy over time integrated impacts these states. So pretty interesting. We get these three eigenvalues that they're not reaching an asymptote per se. They are growing as we integrate more forward in time. This fourth eigenvalue, though, is obviously really pumping energy into the system as we integrate further forward in time. So this eigenvalue 4 is what we're going to actually pluck out and use for the dominant mode analysis here. And so its associated eigenvector, we can essentially get analysis on what states of this ellipsoid is harder to control versus easier to control. And so we can easily see angular rate is going to be the most sensitive, but it's also the easiest control with respect to the amount of energy it requires to move the cart to actually move that pendulum, right? The cart position, though, requires more energy to move, and just physical intuition, that kind of makes sense. So this is a nice side-by-side plot, and it kind of gives us a little bit more intuition when we start going into state feedback control, looking at what modes we perhaps want to control at a higher degree or fidelity versus other ones that might be perhaps a little bit easier, especially with these under-actuated systems. Okay, so this last part here, we're going to step into state feedback control. And so I'm using Mermaid, which is kind of a nice little diagram tool. It looks a little bit different than your standard block diagram, but I think it's okay. So this is your, standard. This is following like Skogestad and some other textbooks, moving this controller gain above, not on the feedback path here in the bottom. So essentially we got the reference signal coming in, summation, we get this error signal plucked out. The K basically amplifies, trying to do state correction based off of this error signal here, R minus Y. We get a U control law, and then that's what gets fed into the plant here, Z dot AZ plus BU, Y is equal to CY, or CZ, sorry. And then the output Y, that's just one-to-one with this output block. So I basically stepped through that. I am using a positive sign convention for the controller gain, and this is in line with Stephen Boyd, LMI textbook, and I think some others. I think maybe Skogestad as well versus minus or the other side. it doesn't really matter. The numerics obviously line up fine. In terms of the LMI, just flipping the sign convention and the way that it propagates out of my solvers, it's positive. So yeah, the gains recovered from the synthesis of the LMI, which I'll go on down here. And so the standard closed loop feedback right now without the observer C. So right now, assuming that I matrix that I talked about earlier, or even just kind of ignoring it, the Y could just be X. It's just 1 to 1. We can get this state feedback here, closed loop state feedback A plus BK. Just using some substitution math here, we get this closed loop state feedback there. And so this is where I'm talking about where the state action space, or this discrete action space, is a 1 and a 0 based off of the carts moving to the right or the left. And that's why I kind of said it's a little bit like bang bang control, when you just kind of maximize the control authority at like one time step, kind of like a satellite and optimal control a little bit. So this is just a quantization step here, which I'll use for when we actually simulate the Cartpole later on. So I put that in here, what this quantization is actually doing. So if it's greater than 0, 1. If it's less than or equal to 0, 0. And that's going to be what's going to be applied at that time step. Okay, so the LMI state feedback here. So this part here is the standard form of a linear matrix inequality. At a first glance, if you're unfamiliar with it, it seems pretty like esoteric and weird. But it's essentially this Z here is our decision vector, and what's really being applied is a matrix pencil. So you basically can imagine like this sort of operation where Z variable here that's packed into like this symmetric matrix. You can pluck it out and then multiply it by another symmetric matrix F, and then you sum that over time, and if that result is positive semidefinite, then we have a suitable LMI. So it requires a linear mapping or operator in between, which I handle. It's hidden right now just because I don't want to dive too much into the weeds, but and then it's this so it's basically scaling this symmetric basis, and then summation over that plus F naught, which would just be kind of like a bias in some ways, which is that F operating on Z. So the state feedback problem for the continuous time feedback is basically finding a suitable controller that satisfies Lyapunov stability. Like if you were to get rid of this BK with the autonomous system, I have it right here. So there exists this P matrix, the Lyapunov matrix, and the standard Lyapunov certificate, A transpose P plus P A less than 0. So strictly positive, or I guess it'd be negative definite. So this is just, instead of A being an autonomous system, we have the closed loop feedback that we put in. And so it has to abide by the same principle here. Note in the standard form here, this is not convex. It's bilinear in P and K. So when you actually multiply the P into this parentheses and distribute the P, we get this bilinear term in P and K because we're trying to solve for both of them. So, but we can update this and make it convex by applying a change of variables here. So let Q be P inverse. P we know is positive definite, so that's okay. And then Y is equal to KQ. And so this next part is applying a congruence transform with the Lyapunov inequality up above. And the congruence transform is essentially preserving like the geometry of the space, different than the similarity transform, which would be invariant with the eigenvalues or the eigenspace. And so the Q here must be positive definite, which because it's a surrogate variable equal to P inverse. And so then if we essentially substituting in the y, we can reduce it to this next LMI here, where our y transpose b gets broken out. We've canceled some terms, and then we get this, nice AQ plus QA transpose on the left-hand side. And then, so we're solving for this directly, as well as ensuring that Q is positive definite. And so the static controller gain can be backed out by K is equal to Y Q inverse, because we have this Y is equal to KQ, and this is just basically, we know Q is positive definite. This is acting as our P again, so we have K is equal to Y Q inverse. And so this merged decision vector, because we have two unknowns at the moment, or what we're solving for is this symmetric, this positive definite Q, and this basically full matrix Y. This is just flattened to be in a flattened decision vector space. So what I do is I do a little bit of a homogeneous transform to get into a matrix and then back to a vector. So so that now that we have a convex problem, has two LMI constraints. Right now the objective, as I mentioned above, is just a feasibility problem. So there's no linear weighting term on the trace, or there's no quadratic a QP, for instance, on the optimization or objective function. It's just 0. So find us a suitable controller that satisfies the LMI constraints. And then more information, if you want, you could refer to the LMI book by Boyd. It's a little hard to read, but I think it's probably the best book on this. All right, so now let's actually solve the problem. So this is just some more boilerplate. This is so my solver will return a dictionary of the results, and so this is just getting the the key value pair safely from the solver. And then this is printing off the solver diagnostic, so what actually emanates from the solver core. It is primal dual, conic programming. So we essentially get a complementarity, a primal, and a dual, which is really nice. So we can kind of start to see, what's struggling in the optimization space, what is actually carrying forward really nicely and smooth. It is a, Newton stepping by nature, so it's going to solve very quickly, which is very nice, like on the order of, I think it's less than 10 steps in this one, which is super nice in comparison to like a gradient descent, which can be much longer because it doesn't have that Hessian, the curvature of the problem. And then equality here, I don't think we have anything. So we don't have any like null space requirements here, so this is just going to be like 0 pretty much. And the one thing at the moment is this global regularization epsilon. I have it set to 1e minus 8. By default, it's 1e minus 12. And so part of this problem is ill-conditioned somewhere. So I applied Tikhonov regularization, a little bit more of a dynamic stepping thing. But if I don't do this, there's going to be a numerical error in the solver, annoyingly. When I do 1e minus 8, I think even 1e, maybe 9 works too, or 10. Anyways, it's just applying more regularization, giving the solver a little bit more curvature. And I think just talking out loud, it could be because it's a feasibility problem. It also could be because it's underactuated, and I didn't step through this up above, but the A matrix here is degenerate. And that's not the full story, but it does add in a little bit to when we factor, not to get too much into the weeds, but when we're factoring in the solution space, we get some sort of ill conditioning. So just bump the regularization up to get more curvature, essentially. Um, yeah, so then I pass in this config, the solve state feedback. We use A and B. We don't care about the C at the moment. And then I'm going to print off the controller gain K here. So wicked fast, 11 steps, optimal, no events indicating like anything that's like precision related or any like warnings from the solver. Here's the primal and the dual objectives, and so that would be, and since we're essentially just having it be 0, it makes sense that it's basically 0. And as you know, the dual would be it's basically a complementary slackness here. So the primal and dual, it's like this inner product that we have between the two of them. That kind of emanates with this mu here, with the complementarity here. So you can see that's very small. And then the residual norms are also incredibly small. Like mu is just 0. Like we said, there's no like null space requirements or constraints rather. And primal dual 1e minus 10, very small. So we have this controller here that we've synthesized now from this LMI above for the Cartpole. So now let's actually just do a closed loop analysis on it, right? So before, when we plotted the poles, we saw we had some right half plane poles and some at the origin. So the intuition here is that these should all be strictly on the left-hand plane. But there's no real like pushing these poles further left or any like tuning of the poles. This was just a feasibility. Give us some poles, give us a stable closed loop system based off that LMI above. And yep, so our closed loop system is stable. We have two, poles here that are a little bit closer to the origin. So if we wanted to push them out, we would want to, obviously probably tune the objective a little bit more, maybe apply a different control technique. So that is this part 3 of the Akreon tutorial series. Thank you for watching, and I hope to see you in the next one.